Hello class, this is Mr. Hart, and in this podcast we want to start our unit on thermal energy. And if you remember back to our unit on energy, we talked about all the different types of energy: potential energy, kinetic energy, and if you remember that thermal energy is kind of the energy of heat or the movement of particles in the air and such. Okay, so we started with a lab this unit where we just learned how to measure temperature with a thermometer and we measured the cooling of water. But today we want to focus on what is thermal energy. What is it actually doing? Okay, so we think of thermal energy. You probably are familiar with thermal energy, right? You've felt something that's hot. You've felt something that's cold. You've seen the temperature of something. You know when it's cold outside at certain temperatures. You know it's hot outside when it's certain temperatures. Okay. But in physics, we have very specific definitions for these things. So in English, we like to think of heat and temperature as being the same thing. They're related, but we don't describe them as the same thing in physics, okay? Specifically, we think of heat as the actual energy of molecules, or what we call thermal energy, okay? That's heat, okay? You can put energy into object. You can put heat into an object, okay? And then temperature is the amount of heat in that object or fluid. So for example, if I have an object that's 70 degrees Fahrenheit, okay, and then I add heat to it, then its temperature will go up to, let's say, 75 degrees Fahrenheit. Okay, so temperature is the measurement of how much heat's in that object. Heat is the actual energy that we're putting in to it. Okay, now the reason we get these confused very often is because we often describe things as being hot, which kind of sounds like heat. Okay, but something being hot is actually a measurement of temperature, not heat itself. So before we get into this, we just need to be able to do some very basic temperature conversions, because a lot of the problems we do in physics are usually measured in Celsius, which a lot of students aren't familiar with. Okay, so let's just make sure we got the basic conversion down. You probably learned this in like 6th grade or somewhere like that, but let's just review. Okay, so the temperature in Fahrenheit is equal to the temperature in Celsius plus 32. Okay. So T is always temperature, capital T. And then the F is always Fahrenheit. And I can never remember how to spell this. I think that's right. Forgive me if that's wrong. And then Celsius. Okay. That's an S. Okay, there we go. Anyway, so the temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32. Okay, so let's say you're given a problem and it's given in Celsius, and then you are trying to kind of think about that in terms of Fahrenheit. Okay, then we're going to use this equation to do that. Okay, let's go ahead and try an example problem. Okay, and this one's a true story. This is actually from me. I was on an airplane to Australia. The captain comes on the intercom and he says, "All right, we're landing in Sydney Airport. The temperature is 25 degrees." And I'm like, 25 degrees? You're telling me it's, snowing in Sydney, Australia? But I forgot, in Australia they don't use Fahrenheit, they use Celsius. Okay? And they don't even say it, they just say 25 degrees or 30 degrees. Okay? So I had to think about, what is that temperature in Fahrenheit? Okay? So what we need to do is, we're given the temperature in Celsius. So our TC is 25 degrees Celsius, and then we just use that equation. So temperature in Fahrenheit equals 9/5 times 25, okay, plus 32. Now if you do 25 times 9/5, you can do that in the calculator, or you can see that 25 divided by 5 is 5. 5 times 9 is 45, plus 32 is 77. So that would be 77 degrees Celsius, or Fahrenheit, I mean. So you could have also done that on the calculator if you want to double check. Okay, but we get that 25 degrees Celsius is the same as 77 degrees Fahrenheit. Okay, simple enough. So hopefully you probably learned that in like 6th grade, so hopefully that's not too hard. Let's go to a different conversion that you're probably not as familiar with, and that is Kelvin. Okay, and the Kelvin scale is an absolute scale. It comes from the idea that absolute zero is 0 Kelvin, but it actually has the same marks as the Celsius scale. So 1 degree Celsius is the same as 1 Kelvin. They just start at different points. Okay, so that's why we add this offset right here. So Physicists don't like to give Kelvin a suffix because they think of it as the absolute scale. So if you just see T, that's temperature, but that is temperature in Kelvin. Okay? They don't put a suffix for K. They just think of it as being the absolute scale. Okay? So that's temperature in Kelvin. Okay? And then that's temperature in Celsius plus 273.15. Okay? So basically it acts the same way as the Celsius scale. The only difference is they start at different spots. Kelvin starts at the 0 being 0 Kelvin or absolute 0, right, where all molecules stop moving. Celsius starts with 0 being the freezing point of water. Okay, so they have different starting points, but they scale the same way. Okay, so we just got to remember that number, 273.15. So let's try an example problem. So liquid nitrogen holds a temperature of negative 196 degrees Celsius. What is that temperature in Kelvin? Okay, so what we do is we just say, okay, that temperature is just going to be the temperature in Celsius plus 273.15. Okay, so we just do negative 196 plus 273.15. So we put that in our calculator, and we get that that is equal to 77.15 Kelvin. Okay. Now keep in mind with Kelvin, you don't actually have to put degree symbols. You just put the K. You don't have to put degree Kelvin. Okay. But there we go. So simple enough. Hopefully that helps you to be able to switch between the different types of temperature scales for the different physics problems. Again, usually you'll be given a Celsius measurement, and then you'll have to switch to Fahrenheit and Kelvin as needed. All right, so let's move on to what's actually happening when heat is transferring between systems. Okay, and so there's two big things we need to realize about why heat gets moved. Okay, and that's because of the state of thermal equilibrium. Okay, so thermal equilibrium is when two or more objects reach the same temperature. Okay, meaning the table and the floor want to be the same temperature, so they'll move heat between each other until they get there. Okay, thermal equilibrium is the state that all objects want to be in. Okay, so until they get to that state, they're going to transfer heat to each other. Okay, so that heat energy is going to move from the one object to another in order to reach thermal equilibrium. Okay, so for example, I put a hot pan of water on the table. Okay, and that hot pan of water is obviously has a higher temperature than the table does. So until they reach the same temperature, that pan's going to keep transferring heat, okay, to the table until it gets to that point. That's what cools it down. So for all objects, that heat transfer is going to depend on two things, okay? And that's going to be the temperature of that object and its conductivity, okay? So you want transferring of heat, okay? You want something that has a very high difference in temperature and a very high conductivity, okay? So for example, I usually do this with my students in class is I say, okay, put your hand on the metal part of your chair. Okay, so they reach down, put their hand on the metal part of the chair, and it feels very cold. Okay, then I say, okay, now put your hand on the wooden part of the table. Okay, and that doesn't feel cold at all. It feels pretty warm. Okay, and then I ask the students, are those things the same temperature? Okay, is the wooden chair, or sorry, the wooden table and the metal chair the same temperature? Yeah, they are. They've been in the same room the whole time. Okay, they've had the air circulating, so they're pretty much at the same temperature. The only difference is the metal is a very high conductivity for heat, wood is not. Okay, so because metal can conduct that heat, what it's going to do is it's going to say, hey, I'm colder than your hand is. I want to transfer that heat so we can be at thermal equilibrium. So the reason your hand feels cold is because the heat from your hand is being transferred to the metal. The sensation of feeling something being cold comes from heat leaving your hand. Okay, that's what makes your hand feel cold. It's not because the object itself is very, coldness. It doesn't have a measure of coldness to it. It's just transferring that heat from your hand. It's absorbing that heat. Okay, so your fingers, right, and your thumb and all the parts of your hand are going to start transferring heat to that metal pole. Okay, because it has very high conductivity, it's going to do this very fast. Compared to the wood, if you put your hand on the wood table, the wood doesn't have a very high conductivity. It's still going to take some heat, but it's not going to do it as quickly, so it doesn't feel as cold, even though it's the same temperature. Okay, so keep that in mind. It's not just temperature. Okay, it's temperature and the conductivity. Okay, another good example of this is if you take like a cake out of the oven. Okay, if you've ever baked a cake, obviously you have to wear mittens on your hands so you don't burn your hands when you grab the metal. But if you took that mitten off and touched the cake on top, you probably could put your hand there for a while. It's not going to burn. It's not going to sting or anything because the cake itself doesn't have a very high conductivity. So your hand can sit there even though the cake's the same temperature, 400 degrees Fahrenheit or whatever you cooked it at. Okay, it's not going to transfer that heat as fast so it doesn't feel as hot. Okay, so this is a very important idea for heat transfer. They want to reach thermal equilibrium, but they have to have a change in temperature or a difference in temperature and a high conductivity to do so. So with that being said, let's quickly go through the 3 types of heat transfer. This also hopefully is review from like an 8th grade science class. Okay, but the 3 types of heat transfer are conduction, convection, and radiation. Okay, the most common type that you're probably familiar with is conduction. That's when heat is transferred by direct contact with an object. Okay, touching the metal pole. Okay, touching any type of object with your hands. Okay, 2 objects being next to each other will transfer heat. Okay, that's all conduction. Okay, convection is when heat is transferred by mass movement of molecules, usually in a fluid. Now that can be air, that can be water. Okay, boiling pot of water is convection. Okay, air circulating through a room is convection. Those also transfer heat. Okay, and the last one is radiation, and that is when heat is transferred by electromagnetic waves. Okay, so light, right? The sun heats up the whole earth with light. Okay, that light doesn't have to travel through air or any type of medium. Okay, but when we absorb that light on the earth, that's what heats the earth up. That's how we stay warm. So really quickly, let's go through these. Again, conduction is when you touch things. That's why you have to wear a mitten when you try and pull something out of the oven, right? Because otherwise conduction would transfer that heat very quickly. Okay, so you have to have some type of insulator between your hand and the pan. Okay, convection is the circulation of fluid, water or air or anything like that. Okay, hot air will rise, cold air will sink, and hot water will rise, cold water will sink, right? And it will circulate as it moves, and it transfers that heat as it moves. Okay. Radiation is how we feel heat from sources of light, like a campfire or the sun. Okay, there's also some convection that happens with a campfire as well, but usually most of the heat you feel is from the radiation from the campfire. Okay, and again, the sun keeps the earth warm. Okay, that's a very important type of radiation. Okay, that light being absorbed. So let's go through a couple of examples of this. For example, with your house, when you have a furnace, okay, or air conditioning, convection is going to be the primary way that your house gets heated, right? The warm air will rise in your house. It will hit the wall and windows, and it will cool down from the outside temperature, and that's what will cause the air to fall back down and circulate through your house. Okay. If you notice, your heater in your house probably is in the basement. Okay. They do that intentionally because they know that that hot air is going to rise. Okay. And so they want the heat to go up. If you put it on the top floor of your house and it was heating up there, nothing would happen to the basement because all that hot air went up. It didn't go down. So you usually have the furnaces on the bottom floor. Likewise, if you have like a swamp cooler for air conditioning, you'll notice that they put it on the top floor on the ceiling, right? Because they want all the cool air to come down through your house. Okay, so that's intentionally designed. That's not just tradition or anything. Okay, they know what they're doing when they put those in your houses. Okay. Another example of convection is the canyon breezes. If you've ever been up like Provo Canyon, you've probably noticed if you go up in the morning, it's very windy, and if you go in the evening, it's also very windy. Okay, that's caused by convection because in the morning, the air moves up the trail because it becomes heated near the bottom because the sun is coming up. Okay, the sun starts to heat the air and it goes up the trail, and then likewise, when the sun starts to go down, the air becomes cooled, so it goes back down the trail. Okay, so that heating from the sun in the canyon causes those high canyon winds and breezes, okay, in the morning and in the evening. Okay, similar thing on the ocean as well. If you go to the ocean, the most windy times on the beaches are in the morning and in the evening, okay, for the same reason. Convection is also how you keep your body warm. Okay, your body uses 20% of the energy consumed for work to move your muscles around and things like that. The other 80% becomes heat that is disposed of. Okay, that happens through your blood. Okay, your blood is basically a convection system that carries heat throughout your whole body, up your arms, through your legs, to your heart. Okay, that's how you stay warm. That's why we're able to generate so much heat, and that's why our internal body heat's around 98 degrees Fahrenheit, because our blood is what's circulating that for us. Okay, and then last of all, this is hopefully something you learned in like geography class, but radiation is the cause of the seasons. So if we imagine the earth like this and the sun is over here, the light's coming in, the equator will have the hottest parts of the earth and the poles will have the coldest parts of the earth, because the sunlight is not as direct. There's more area that it has to cover per ray of sunlight, I guess you could say. But that's what causes the seasons. More direct radiation right here, less direct radiation right here, and the earth also has a slight tilt. Okay, it doesn't look like this exactly. There's actually a line of tilt that goes right here, and so during the summer this part is facing more towards the sun, which is causing summer in the northern hemisphere, and then on the other side of the world it's their winter at the same time. Okay, so that's how we have this effect. Okay, but that is it for radiation. Make sure you do the homework about all the different types of heat transfer. Let me know if you have any questions, and thank you for watching.